Routing Dynamically, Chapter 7. Introduction. In a large network with numerous networks and subnets, configuring and maintaining static routes between these networks requires a great deal of administrative and operational overhead. Implementing dynamic routing protocols can ease the burden and give the network scalability. Dynamic routing protocols. Several needs through time have made new protocols emerge for several reasons: scalability, IPv6, or others. To address the needs of larger networks, these new protocols were created. Open Shortest Path First, OSPF, Intermediate System to Intermediate System, ISIS, Interior Gateway Routing Protocol, IGRP, or Enhanced IGRP, which is abbreviated as EIGRP. The purpose of dynamic routing protocols includes discovery of remote networks, maintaining up-to-date routing information, choosing the best path to destination networks, ability to find a new best path if the current path is no longer available. The main components of dynamic routing protocols include data structures, which are tables or databases kept in RAM, routing protocol messages, which are used to discover neighboring routers, to exchange routing information and maintain accurate information about the network, and the algorithm. Routing protocols use algorithms for facilitating routing information and for best path determination. This is an example of the EIGRP protocol. Pros of dynamic routing. Routers exchange routing information when there is a topology change. Routers automatically learn about new networks. Routers find alternate paths when there is a link failure to a current network. Dynamic routing protocols require less administrative overhead. Cons of dynamic routing. Dedicating part of a router's resources for protocol operation. CPU time. Network link bandwidth. Networks with moderate levels of complexity may have both static and dynamic routing configuration. Static routing. Static routing has many uses, such as smaller tables in networks that are not expecting to grow significantly, routing to and from a stop network, or accessing a single default route. This is an example of static routing. Dynamic versus static routing. In this table we can see the advantages and disadvantages of static routing. Dynamic routing is better when you have networks that might grow significantly. It might be exhausting to manually set static routes to networks like this. In this table we can see the advantages and disadvantages of dynamic routing. To sum up, dynamic routing is more complex to implement. It requires additional CPU and memory, and it takes up a little bit of bandwidth as well. It is better when we have big networks that might scale or add new subnetworks. And static routing is better when we have easy networks that can be easily configured manually and that might not grow. Operation of a dynamic routing protocol. A routing protocol follows these steps. The router sends and receives routing messages on its interfaces. The router shares routing messages and routing information with other routers that are using the same routing protocol. Routers exchange routing information to learn about remote networks. When the router detects a topology change, the routing protocol can advertise this change to other routers. In this example, we can see how routers exchange updates to fill up their routing tables. Network discovery. Routers exchange updates to find out about new changes to the network. They also exchange routing information. At this point, the routers have knowledge about their own directly connected networks and about the connected networks of their immediate neighbors. The routers exchange the next round of periodic updates. Each router again checks the updates for new information. Instance vector routing protocols typically implement routing loop prevention technique known as split horizon. Split horizon prevents information from being sent out the same interface from which it was received. The network has converged when all routers have complete and accurate information about the entire network. Routing protocols can be rated based on the speed to convergence. Generally, older protocols such as RIP are slow to converge, whereas modern protocols such as EIGRP and OSPF converge more quickly. Routing protocols can be classified according to its purpose, operation, classful behavior, or classless behavior. An autonomous system, abbreviated as AS, is a collection of routers under a common administration, such as a company or an organization. An AS is also known as a routing domain. The Internet is based on the AS concept, therefore two types of routing protocols are required. Interior gateway protocols, abbreviated IGP, used for routing within an AS. It is also referred to as intra-AS routing. Exterior gateway protocols, EGP, used for routing between AS. It is also referred to as inter-AS routing. In this image, we can see how IGP and EGP routing protocols work. Distance vector routing protocols. Distance vector means that routes are advertised by providing two characteristics, distance and vector. Distance identifies how far it is to the destination network and is based on a metric such as the hop count, cost, bandwidth, delay, and more. Vector specifies the direction of the next hop router or exit interface to reach the destination. Link state protocol operation. RIP-enabled routers send periodic updates of their routing information to their neighbors. Link state routing protocols do not use periodic updates. After the network has converged, a link state update is only sent when there is a change in the topology. Classful and classless routing protocols. The biggest distinction between classful and classless routing protocols is that the classful routing protocols do not send subnet mask information in the routing updates. Classless routing protocols include subnet mask information in the routing updates. The fact that RIP version 1 and IGRP do not include subnet mask information in their updates means that they cannot provide variable length subnet masks, VLSMs, and classless inter-domain routing, CIDR. Classful routing protocols also create problems in discontinuous networks. A discontinuous network is when subnets from the same classful major network address are separated by a different classful network address. In this table, we can compare distance vector versus link state protocols. We can see also some different kinds of routing protocols. In distance vector, we have RIP versions 1 and 2, IGRP and EIGRP, whereas in link state we have the OSPF and the ISIS. Distance vector protocols. Distance vector routing protocols share updates between neighbors. The router is only aware of the network addresses of its own interfaces and the remote network addresses it can reach through its neighbors. Routers using distance vector routing are not aware of the network topology. Some distance vector routing protocols send periodic updates. Here, we can see the purpose of the routing algorithms, which are sending and receiving updates, calculating the best path and the install route, and detect and react to topology changes. RIP uses the Bellman-Ford algorithm as its routing algorithm. It is based on two algorithms developed in 1955-1956 by Richard Bellman and Lester Ford Jr. IGRP and EIGRP use the diffusing update algorithm, dual routing algorithm developed by Dr. J. Garcia Luna Aceves and SRI International. In this table, we can compare the IGRP and the EIGRP protocols. We can see that the EIGRP is better than the IGRP in every way. This is logical because the EIGRP is an improved version of the IGRP.
RIP and ripping routing. RIP means Routing Information Protocol. RIP version 1 is a classful routing protocol for IP version 4. To enable RIP, we must use the router RIP command, and RIP routing for a network, we use network and the network address in router configuration mode. To disable or eliminate RIP, we use no router RIP, and this command will erase all configurations of RIP and stop the process. Show IP protocols will display the IP version 4 routing protocol settings that is currently configuring the router, and using show IP route will display the RIP routes installed in the routing table. By default, RIP process is configured to run version 1 RIP. We use version 2 on the router configuration to enable RIP version 2. This is a classless routing protocol compared to the classful RIP version 1. To modify the default RIP version 2 automatic summarization, we use the no auto summary router configuration mode command. RIP updates really only need to be sent out through interfaces connecting to other RIP-enabled routers, because these can consume bandwidth and weight resources as well as security risks. We use the passive interface configuration mode command to prevent the transmission of RIP routing updates through a router interface. And we use default information originate to instruct the router to propagate the static default route in RIP updates generated in the interface. As RIP also exists in IP version 6, we must enable IP version 6 unicast routing, and instead of using network address command, we use IP version 6 RIP and domain name enable to configure a network address. Link state routing protocols are also known as shortest path first protocols, are built around Etzger-Dijkstra shortest path first algorithm. We have two protocols of IP version 4 link state routing, which are open shortest path first and intermediate system to intermediate system. We enable open shortest path first by using router OESPF and process ID. Dijkstra is an algorithm that uses the cost of each path from source and destination and determines the total cost of a route, and then compares with other routes and takes the one shortest. Cisco implementation for the metric is the bandwidth of the outgoing interface. The process of link state routing is: first, each router learns of each of its own directly connected networks and says hello to its neighbors. Then every router sends a link state packet, or LSP, containing the state of each connected link. Then it plots with the LSP all the neighbors so they can store the data in their database. And then with the database they construct the map of the topology. With each cost, it generates the best path to each destination network. Here we can see the shortest path first tree using the database of every router, and each router casts its own shortest path first tree independently. They build it with the data of other routers, but each router has. There are advantages and disadvantages of link state routing. Advantages: each router has its own topological map of the network, and it can determine the shortest path without other routers sending information. By immediately flooding the link state packets, it achieves faster convergence. And if there is a change of the topology, they are only sent to change each router database and compute a new SPV tree and determine a better route. A disadvantage of this is that maintaining the link state database and SPV tree requires additional memory and CPU processing, and bandwidth can be affected by this flooding of LSP The routing table. An ultimate route is a routing table entry that contains either an X-hop IP version 4 address or an exit interface. This can be directly connected, dynamically learned, and local routes. A level 1 route is a route with a subnet mask equal or less than the classful mask of the network address. A level 1 parent route is a level 1 network route that is subnetted. This can never be a ultimate route. A level 2 child route is a route that is a subnet of a classful network address, and these are also ultimate routes. Route lookup process. First, if the best match is a level 1 ultimate route, then this route is used to forward a packet. If the best match is a level 1 parent route, then we proceed to the step 3, that is, we match it with a level 2 child route. That subnet is used to forward the packet. If there is no match with any level 2 routes, then we do a lesser match with a level 1 supernet or default route, and then we forward the packet, and if there is no match, we drop the packet. The best route is the longest match. The best match is the route in the routing table that has the most number of far left matching bits in the IP version 4 address. The route with the greatest number of left bits that matches will be always the preferred route. Also, the IP version 6 routing table is very similar to the IP version 4 routing table. It is populated using directly connected interface, static interface, and dynamically learned routes. Because IP version 6 is classless by design, all routes are level 1 ultimate routes. And we use the show IP version 6 route to display the routing table